thanks for coming. So this talk is Bregman divergences are good, actually. And it's going to be really on scoring rules. Daniel asked if I wanted to give a talk on just kind of like some of the Bayesian talks on introduction to scoring rules, but Daniel and I also have a project on scoring rules for alignment. And so I'm trying to give the presentation, kind of accomplish both goals as gearing this towards the teaser at the end of the connection to alignment. So what are scoring rules? Well, like traditionally you think of them as a tool for evaluating the quality of like a forecast or a probability distribution. So you give a forecast, you say like, hey, here's my probability of rain each day or something, or whatever, and in general, the higher the probability of trues, and the lower the probability of falsehoods, the better your forecast is. Right? You want to forecast high probability for true things, low probability for false things. So here are some examples of scoring rules. You could just take the absolute value, the difference between the forecast of some event, x, and whether it's true. Yeah.
Is pi the forecast?
I'm using pi for probability distributions for notational reasons that will probably emerge later if I get deep into the talk. So yeah, think of the Greek lowercase letters as probability distributions.
And omega is the true one.
And omega is the world, yeah.
Okay, right.
So yeah, so omega x is 1 if true. Yeah. All right. So you just take the difference between your forecast and the actual truth value and sum them up. It's the absolute value score. You could take the Euclidean distance. You can take the Breyer score, which looks very similar but isn't, and you could take entropy.
Isn't the Breyer score just the Euclidean distance squared, or am I missing something?
It's going, yeah, you'll see actually, it's going to come up important as an important thing, yeah. The Euclidean score is bad, the Breyer score is good. Because only the Euclidean score is proper and the Breyer score. Sorry, the Breyer score is proper and the Euclidean score is not. Yeah. So scoring rules, you can think about them in a lot of different ways. I can't get through all of them, and they can do a lot of different cool things for you. One thing, as we'll see, is they can be tools for eliciting credences. So if I want to know what your credences are, I can use a certain class of scoring rules. And then if I say I'm going to pay you, and we're going to find out the truth later, and you'll get paid according to the scoring rule, then with the right class of scoring rules, I could get you to tell me what you actually think, like how confident you really are. In fact, actually, you can do it with multiple choice exams if you're a professor, and you want people to just get credit for guessing right, you can score them based on their probability distributions, and they should actually just tell you how confident they are in each of the answers. Right? So it's a very useful tool. Likely, right, tools to evaluate forecasts. The idea is, right, I say like, look, you gave this epistemic thing, how confident you are in each thing, how well did you do, measures of inaccuracy, how far away you are from the perfect forecast, where you give 1 to all truths, 0 to all falsehoods. Measures that we think of as purely epistemic disutility. So like a big thing in philosophy was sort of decision theorizing epistemology. The idea being my goal is to believe true things, disbelieve false things. And so if I want to say, here's like a way of reasoning, I should justify it in terms of like, if you follow my rule, that's a good means towards having true beliefs. And I can prove it by using scoring rules as like your disutility function. And generalized information and entropy measures, which I also won't focus on too much, but you'll probably get a sense of if you're familiar with that stuff. It will kind of, I hope, become somewhat apparent, the connection there. All right. So the focus I'm going to do today is, I think, one that's a little bit anathema to a number of philosophers who like these, but I'm going to think of it as a scoring rule, or the good kind of scoring rules, as measures of the expected practical disutility of a forecast. The idea being, I'm in a certain epistemic state. I have some beliefs, or some partial beliefs, some credences, and I'm going to use those as I go about my day. And because I don't have credence 1 in all truths, credence 0 in all falsehoods, I'm going to make some good decisions, some bad decisions, right? Some things that like I could have done better if I had known exactly how the world was. Do some things that I could have done. I did the right thing sometimes, made the exactly right decision, and so on. And so because I'm in this epistemic state, I expect to lose some utility that I could have gotten if I were perfectly confident in all truths. And then this is kind of, I hope, foreshadowing, if we can get to the AI stuff towards the end, thinking about when I would want to outsource my decision making to someone else, given my views about them. So maybe I don't know exactly what Daniel thinks, but I would think, under what conditions would I say, Daniel, you just like get to act as my agent? I think that you would do that because you have like more accurate credences, and maybe your interests are pretty aligned with mine. I'm willing to just like let you act as my agent, make decisions on my behalf. I'm also going to say, like, this is going to tie together a lot of work from different places with different people, and I'm going to be very bad about remembering to credit people at various times. So follow up with me if you're interested in anything in particular. All right. So today we're going to give a basic sense of how scoring rules work. I kind of want to walk you through the basics there. Construct scoring rules. In this way I was kind of motivating as expected disutility of a forecast. Going to generalize that to random variables. We're going to start with events and then go to random variables. And then connect to the deference and outsourcing decision making angle. And I hope have the teaser for this project with Daniel on sort of what you think of as maybe measures of tolerable misalignment, when maybe if we're still somewhat misaligned, I would still, under certain conditions, be willing to outsource decision making. Right. So let's start with just, again, some basics. Maybe this blue font is unfortunately not quite coming through. You can think of it first as different scores. So there are all these different scores I said. So like, what's the difference between them? Well, you can think that they all care about having, high probability in true things, low probability in false things. But they measure, like, that doesn't really pin things down uniquely, right? And so they measure different types of goodness. So you could think, let's say A is actually John. Here, Alice and Bob's forecasts. Bob had a higher probability in A. But look, he also has a very high probability. He didn't like spread out his credences, like he's very peaked on this false thing D. And so there's some ways in which Alice is better, some ways in which Bob is better. And so you'll see actually like the Breyer score prefers Alice, the log score would prefer Bob. It's just like log score is purely local. It just looks at your probability in the true thing. Okay. So that's the sense of inaccuracy. What I mean is like how far you are from the truth. And let's just like flash a definition here. So you have an accuracy I can be a function from the probability, some probability distribution over the state space and the actual, some world to the positive extended reals. And we'll say it's truth directed if pi is always no further from the truth than rho in absolute terms, then pi gets a better score, a lower score than rho.
So what is rho again?
Rho is just, I'm using the Greek letters to specify a probability distribution, so there's something inbuilt in it. And I'm going to say that's just definitional for what it takes to be a scoring rule. Okay. Some scoring rules, this is from this morning, have a special property called propriety. The first try, I thought pretty good. So for a proper scoring rule, the idea is each probability function, if you have a probability function, in expectation, it assigns itself lowest expected score. And we'll say strictly proper if it's like uniquely lowest. So the idea is like, if I have a forecast and I use like, we'll say the Breyer score, I always expect like, that's in expectation the best forecast. I don't think that some other forecast I can directly specify. Like I say, like, well, I have credence 0.7 in rain, but I would think I would actually be closer to the truth if I had credence 0.8 in rain. Right, so if I did that, that would not be proper, but for this it is proper. Yeah, so like what I just said. If in expectation, pi always will do best by its own lengths. So, from the ones I flashed earlier, yeah.
So what's the relationship between truth directedness and propriety?
So you need more, so all proper scores are truth directed, but not all truth directed scores are proper. So everything. And so this is going to be very easy to show if you just take derivatives. Right? It's like, you can convince yourself this is the difference between Euclidean and prior.
What's strict? Oh, no, I think it's obvious.
Oh, strict, just that you yeah. So, in philosophy, this is a bit of a problem because, right, you think like the core thing is that what I want is accuracy. However, nothing really works if you don't have a proper scoring rule. Like you can't. So, for example, we have arguments in philosophy like why should you be probabilistically coherent? Why should your credences, your partial beliefs obey the axioms of probability? And for any continuous, strictly proper scoring rule, that is, if you're incoherent, there's going to be some coherent measure, so coherent probability distribution that is less inaccurate than you, strictly less inaccurate than you, at every single world, right? So you're kind of leaving epistemic money on the table. The problem is it doesn't work if it's not proper. It's not strictly proper. So you can't just use truth directedness and get the arguments to go through. And there aren't like kind of great, if you're coming from that starting point, there aren't like great, watertight arguments for propriety. So I'm going to go from like a completely different, not epistemic starting point. I'm going to go from a purely practical starting point. And that's from, the statistician Aiden was just plugging, Mark Schurch. This is my sort of read on the paper he gives. So the thought is this, right? Like I just said, I have my epistemic state. I have some beliefs about the world, some partial beliefs about the world. I'm going to go about my day. I'm going to make some decisions. Some things are going to go well. Some things are going to go badly for me. And the thing is, I don't know what decision problems the world's going to throw at me. So I have some distribution over what those problems will be. And when I average out, when I integrate over that, that's going to give me my scoring. So let's kind of walk through how that actually is gonna work. So the inaccuracy, the way I'm going to gloss it, there are many different ways you can kind of build these and construct these. The inaccuracy of your credence in X in a proposition. I'm gonna say proposition because I'm a philosopher. What I mean is event. X is when X is true or false, is the expected disutility of having a credence of X, given that X has that truth value. Right? Like in the world where X is true, I make some bets, I'll sometimes lose money if my credence isn't 1. And if X is false and my credence isn't 0, I'll sometimes lose money. And then here's kind of, I hope, starting to foreshadow a bit. If I'm thinking, how good is Daniel's forecast for me, or a particular forecast of Y, that's the expected utility of using, if I kept my preferences the same, but I use that forecast to make decisions instead of my own, how much I would expect to lose with that forecast instead. Yeah.
Do you get trickiness if your utility function depends on your beliefs explicitly?
Probably. Yeah. Yeah, I'm kind of going to assume a mostly no funny business there clause, but yeah, I imagine you could probably get some sort of thing happening. So this is kind of the sense of assume perfect alignment. We have the exact same preferences. Daniel and I do, we always get the same payoff at each world, but Daniel has a different probability function. How much would I expect to lose? If I knew his credence is Y, I keep mine at X. How much would I expect to lose? So just think it through. And then the Schurch construction, let's see, loses some generality. It's going to allow us to construct what we call local scoring rules, where I score an individual forecast in a single event, and I can make it a global one by just adding. But it's not going to be kind of fully general. We'll see some. We're going to generalize it next. So local score is just we have a probability between 0 and 1, and a truth value of either 0 or 1. And extended to the extended reals. And then for truth directedness, right, we just have this like weak monotonic increasing. So some examples. Okay. So let's start with like a single problem. Oh yeah.
Why do you need infinity?
Well, the log rule will give you a score of you're infinitely bad if you have credence 0 in a proposition that's true. So you want to have, and that's like an important one because you know. Yeah.
So like before we were talking about the Breer score, which like if there's one thing that happens and there's two alternative possibilities, the Breer
Right,
score,
yeah.
the Breer score depended on like how I allocated my credences over the two things that didn't happen.
If it's a global one, yeah.
Yeah. So why am I not caring about that anymore? Is it bad to not care about that anymore? Maybe?
Well, here it's just like I only know like one forecast you have, and I'm scoring that single forecast. Yeah. I mean, it's probably like more interesting when you look at like more than one forecast, because we all agree for a single event what forecasts are better at a world, right? The ones that are like closeness to truth does kind of determine everything, but like for Sturvish, you're kind of building things up from the local scores to make the global score.
Okay. But I mean, even with Breer score for a single event, right?
Yeah.
It's like
X minus I squared.
yeah, which is different from like sum over ways that event could have happened, X minus I squared.
Yeah, but you're thinking like out of world, that's all going to be fixed, right? So it's like out of world, like I have some propositions, they're always all fixed.
They're just propositions.
They're just still just
they're not like 3 outcome things. They're just like
2 outcomes.
they're just true or false.
True or false, yeah.
Oh, okay, cool.
Yeah, we're gonna go to random variables later.
Oh, okay, yeah.
Okay. So like let's first just take I here have no uncertainty about the decision problem I'll face. Here's the decision problem. Alice is deciding whether to take an umbrella. If it rains, she'd rather have it. If it doesn't, she'd rather read it at home. This is always like a standard thing. It's like the most boring. All right, so like imagine these are her payoffs, right? If there's rain and she takes the umbrella, it still kind of sucks because it's raining. If she has no umbrella, it sucks more. She has an umbrella and it doesn't rain, it sucks because she's lugging around an umbrella. And if she has no umbrella and no rain, that's great. So we're gonna do so notice, right? If we're thinking about like how much utility Alice is actually gonna get, if you just kind of like work this out, you'd see all that matters is whether it rains, the state of the world, and whether her credence is above or below 2/5, right? Like if she has credence, 0.8, and she moves her credence to 0.9, like nothing, that's like useless information for her, right? Because she's gonna do the exact same thing. So it's just what side of this border you're on. And so we're gonna kind of normalize everything to make this easier to work with to construct this square. So we're gonna minimize expected loss instead of maximize expected utility. So just put a negative in front of multiply everything by -1. And then normalize the problem, like in the rain problem, she's automatically losing 1 util no matter what, because it rains, but like that doesn't matter, right, for decision making. And then divide it out. So here's kind of how this will look right now, right? She gets payoff 0 when she brings an umbrella and it rains. No umbrella doesn't rain, that was the right decision. And then here's how we look, right? This 2/5 being very prominent. And forget about the 5, that's like the stakes of the decision, how important that particular bet was to get right. Alright. And again, like now, kind of just harping back on this point, imagine instead, I said like, well, like if we paid Alice $1 to get herself, she's at 0.5 to make herself, more confident in rain, would you take it? Like, sure, what does she care? Because she's going to make the same decision in that case. Right.
Sorry, you threw away some information there, right? So you like lost the information about Alice's preferences between the diagonals, but you're saying that this is a decision relevant, so we can throw it away.
The preferences between the diagonals.
Yeah, I think one was -1 before, right? They were not equal before, they're now equal. Is that right? Or am I missing something?
Rain and umbrella versus
when I normalized her.
Yeah. Like she had a preference between these, and now she doesn't.
Oh yeah, but that's because that doesn't affect your decision.
Yeah.
She's like, there's a guaranteed util loss in the rain world.
Yeah.
Yeah. So like in some sense it's losing information, but nothing that affects the decision.
Right.
All axate independence here is also just basically the same. Yeah, it's all just bets rather than okay. So like you can make a score here for Alice. Right, here's a scoring rule. It's merely proper. In the let me just double check.
Sorry, was merely?
Merely means like she thinks some other credences are just as good as her credence.
It's not strictly.
Oh, it's not.
Yeah, not strictly. Yeah. So in the world where it rains, like what happens? Well, she'll lose nothing for any credence loses nothing if it's above 2.5. Otherwise, it loses 3/5. Yeah, that's this score. Right. So it's a merely proper scoring rule. Maybe not a very interesting one. Truth directed. Yeah. So like let's generalize this a little bit, right? We're gonna say that there are two decisions. She can do D1 or D0, and there's some cutoff point here, and some stakes between 0 and infinity. Every decision matters, so it's can't be 0. And so we're gonna just kind of represent everything in this form. Right. All right. So you'll do D1 if the forecast is above Q, and knowing Q is, let's call it a Q problem. Knowing Q is then sufficient to characterize the problem. Any two decision problem, with this we'll call a Q problem, or D1. So then you just replace the numbers from before to 1 minus Q and Q. Alright. So now here's kind of like where the magic is going to start to happen. You don't always know what decision problem you'll end up facing. And we need to account for the uncertainty about the value of Q. And there are going to be two factors here. Right? One is the probability density so again it's thinking like she doesn't know what bet is going to be offered. So she doesn't know kind of like where the cutoff point would be, and she doesn't know how important it would be to the value. So if you were to think of it like now on the more general side, right? Imagine there are just finitely many options. We would get her score for 1 is like, well, her expected score here is 1 minus Q for everything where her credence is under Q, times the expected weight, given that it's a Q problem, times the probability of facing that a Q problem. Is that right?
Sorry, what's X again?
X is just the event. Sorry, the proposition.
Okay.
Yeah, like rain, no rain. Yeah.
Right.
Yeah.
Does the probability over Q problems come from somewhere?
That's just what she thinks. Whatever she thinks, it's up to her.
Okay, so
It's her own view.
She also has a
Distribution over
over
that,
Q
yeah.
problems.
You don't have to. Like, you could interpret it some other way, but that's I think she's
X is not the event, X is credence, right?
Big X is the.
So big X is the event we're scoring.
Yeah.
We're scoring her. She's giving a score for that, right?
And then little x is the credence though.
Yeah, and then pi of Q is like the probability that the problem is a Q problem, and then given that it's a Q problem, how important
Sorry,
it is.
W is the importance of the problem?
The is expected. The importance of that problem, the stakes of the problem. Right. So the idea would be like, imagine there are one of two bets you could be offered. The bet is I'll give you $1. I'll sell it to you for 20 cents, and I'll give you $1 if it's true. $0 if you'll lose your money otherwise, right? Or I might give you so I could tell you about your choices is whether to take a bet. I'll sell it to you for $1,000, there's like whether your credence on the right side of the second cutoff point matters a lot more. If I'm scoring, right? What's your expected loss? Like it doesn't matter, the dollar bet doesn't matter as much.
Right. Okay. Okay.
Alright, so nothing like super fancy. When we move to the continuous case, we have to then think still of the weights, how expected, the expected importance, given that we face a Q problem, but now we have to have a density over Q's. And I'm going to call that the support function. Here's like a simplified version of Sherwood. We'll have S1. What we're going to do is, right, we're going to say like, if X is true, so if the proposition is true, then I only lose, in those worlds, I only lose when the price of the bet or something is above, if we were going to normalize everything to $1, is above my credence, because those are the bets I reject that I should have taken. Right, so I just have to integrate from my credence to 1, and what I lose there is 1 minus Q times the importance of that. And I'm going to also discount that by my density over that particular. So it's all getting into the density over that particular problem being faced. And then for 0, it's going to be the same thing, right? It's like these are the bets that I did take when the price of the bet was low enough, but I still was going to lose. So that sucks because it turned out to be false. I lost Q, what I put up front, and then again how important that was. That's sort of and basically for this class of local scoring rules, any local scoring rule you want that's in any way reasonable can be captured this way. Right. So the full theorem, for you fancy people who aren't philosophers, so maybe some of you philosophers are fancy. Fancier people than me, and you like Lebesgue integration and all that. You paid attention in analysis. This is going to be the way you represent it. Yeah.
Sorry, maybe I don't know, but how can a scoring rule be like pair valued? I thought a scoring rule like spat out a real number. How is S equals G1, G0?
Oh, sorry. I should have. So part right here is because I didn't change my notation correctly well enough because I was going to use gambles later. Anyway, so I'm thinking it really should just be S, and then I put this should be S x1 S x0. The score of X, right? You feed it a truth value and credence.
Okay, yeah.
Right. So a scoring rule S, it should just be let S be a left continuous scoring rule. So that SJ, I should have,
So you think of the scoring rule as like a function that when the event does happen, the function the event doesn't happen, and those are just the two different.
Is that?
Yeah, I understand that.
Dan.
So a thing that's kind of weird about this to me is it seems like we have this pi, right? This probability of values of Q, and you're telling me that this is like a proper scoring rule, but it seems like you didn't require pi to be correct for this scoring rule.
No, it just has to be regular, right? So the idea is I think any bet is possible. That's going to make it strictly proper. If I think some region is impossible, then it's going to be merely proper because it doesn't matter if I move about in that region of impossibility.
All right.
But this is up to me, right? This is how I'm going to score my own credence. It's well, if you learned X was true, how well are you going to do? Here's where I would lose things. Here's where I would lose things.
Cool.
So So right, if you think any bet kind of is at least possible, then you'll use a strictly proper scoring rule. If you knew that it was you're facing the umbrella problem given earlier, then you could use a merely proper rule. So that's right, the expected disutility If there's a bet, like your payouts can, your payouts can be determined by some bet or other on whether it rains. You don't know what that bet's going to be. That's how much you expect to lose given your epistemic state, and how much you expect to lose if you had instead had a different epistemic state.
Okay, a thing that seems weird to me about the setting is, if I understand correctly, like, an agent in this setting is saying like, okay, I'm gonna pick my probabilities,
Yeah.
my probability of whether this event is true or not, and then later someone's gonna offer me a gamble, and then I'm basically gonna be compelled to do expected utility maximizing then. So right now, what's my like expected utility maximizing over what my belief should be?
Yeah.
That should be the true one. But like, that's a bit of a weird setting, right? Like you can imagine like, okay, like maybe just after someone offers me a gamble, I can pick my belief, or like I can who knows? Maybe I don't even have to be that expected utility maximizing.
Yeah. I mean, you might want to relax it, but like that's the, if I'm a expected utility maximizer, I don't know like what the world's gonna throw at me. I'm gonna make some decisions, right? Like I don't know, like you can think about it like, right? Like I have some credences and stuff. People are gonna like ask me whether I want to do something. I don't know what sorts of things will be thrown my way later, and but I do have some like idea of it, right?
I guess I don't have a question other than I find that a little bit weird.
Okay.
Alright.
I don't know how to answer that objection. So if you like thought of it here, just like to give you some examples, this is like a very old janky graph I made and didn't bother regenerating, but you could think of it like the Breyer score, right? It's like everything is kind of uniform. You get this Breyer score over the region, over the interval. The log, right? It's like it really matters kind of at the ends, and then spherical. It's like you would think of it as something like binary classification or something, like being on the right side of 0.5 matters. Yeah.
Does the converse hold? Is it the case that, in other words, is it the case that every proper scoring rule is realized as like a distribution of gambles?
If and only, yeah.
Okay.
For these local rules, yeah. Okay. So now you might say, what if I think Daniel is actually smarter than I? I don't know what he thinks. But I know he's like really good at forecasting whether it's going to rain. So he could have a few different credences. What does it mean for him to be, if I expect him to be more accurate on every strictly proper score, right? So you can think about this. This like takes out a little of the weirdness. No matter what my measure is over the interval, like if it's always the case that no matter what it is, so you can think about that as me thinking, in some sense, Daniel is like absolutely epistemically superior to me about whether it rains, because no matter how I go about measuring an accuracy, I expect Daniel to do better. Right, no matter what my distribution over bets is. So you think I'm willing to outsource betting on this proposition X. Anything with a payout, I know it's just going to depend on X. I don't know what the bet's going to be. But no matter what the world's going to throw, I'd rather have Daniel do it than me. Right? Assuming, again, he's completely aligned with my utilities. So there, you have what's called simple trust, which is weaker than reflection. And there's these inequalities that do not collapse to equalities. My probability in X, given Daniel's probability, whatever it may be. So I'm using P here for this like unknown probability. It's in this case a random variable, more generally it'll be a random object. His probability in X is at least X. Mine will also be at least X. And given that his is no more than X, mine will be no more than X for this given X. And the global version would be, because it's an algebra, I don't have to do the second part. And by the way, in case I want to forget, all the theorems here, for this, these deference principles are going to depend on omega being a finite state space. I just don't, I'm again a philosopher, I'm a word cell, so I can't prove things that are too hard, and so I can't do it. It really depends on this like region where you can use it. The proofs all depend on that. I don't know what happens when you move out of that, but I just want to flag that as.
Sorry, can you see the rest? Okay.
Sorry. Simple trust. So it's weaker than reflection. I don't necessarily have to totally defer to Daniel. And maybe, maybe you're gonna say is what this means is also like it might be like my best thing would be like let me first learn what Daniel thinks and then I'll update my credences and I do even better. But like if the choice is just me or just Daniel decides, then I'd rather have Daniel decide. One of the Daniels. So theorem pi expects p to be at least as accurate on every strictly proper scoring rule, if and only if pi checks p. Simply checks p. And just in case you're worried, doesn't this conflict with propriety? No, because I don't know what Daniel's. The p is varying from world to world. However, this is not closed under conditionalization. And even for the global version, and even if you do that by fiat, if you say, well, like, let's just see what happens when we say, like, close it under conditioning, you do get something intermediate, but it's still not going to be enough for me to be willing to outsource all decision making, even if I expect them to do better on every proposition, and we close that under conditioning. There's still going to be gambles I would rather just make myself. Lord. So.
Why is that?
The real reason is something like I'm not exactly in the convex hall of Daniel's possible credence functions and a few other things, but that's kind of the geometric reason. It's not enough to constrain, and that's, well, maybe we can talk a little more about that. I don't know. But that's kind of the basic generating thing. All right, the conic construction. So Jason, he's actually really interested in this, and we're co-authoring some stuff. Also doing scoring rules for imprecise probability. So if you're like, if there are any imprecise probability people here, email Jason, and because he has stuff and he's like under publishing it. So like, get him to like tell you about it. All right. So now we're going to switch things up and go even more pragmatic. So again, we have this finite space, and I'm going to skip some stuff, some details, but we're thinking now, think of a gamble as just this vector that represent my payoffs in every world. So G will pay out utility GI in world omega. And what you can think of is every probability mass function pi will cut the space of gambles in half. So there will be those that pi finds almost desirable given a utility function. So almost desirable meaning at least 0. And we want almost desirable just to get closed and everything. And have the 0 gamble in there as a status quo, right? So the desirable gambles according to pi is just going to be orthogonal to pi, right? The hyperplane that's orthogonal, and there'll be all gambles such that pi I times gi, the dot product, is at least 0, right? So I can characterize pi by instead looking at this dual as this hyperplane that separates these two things. Okay. We'll let M be the set of all the big measurable gambles. Some of these will be precise. You can think of some of them are going to correspond to precise Bayesian models, like if they're a half space, right? And some won't. And now you can just think of it as saying, well, what I really, instead of giving me a probability, all I need is like, what gambles would you take? What gambles look good to you? Right. And we can think of the ideal gambles, right? These are all the ones with non-negative payoffs at a world. So like if there's a heads world and a tails world, at the tails world, this is the space of ideal gambles. And this is it for the heads world, right? Everyone kind of. All right. So what kinds of errors could I make? Well, there are two things that go wrong for me if I'm not ideal. Let's take the heads world. Suppose this is my space of almost desirable gambles, this non-probability thing. I can still score it very well because I have here the gambles in red that I take at the heads world, but that have actually negative payoff. And then here, are the gambles I don't take that I should take. So the error set you can think of as just the symmetric difference between the gambles I take and the ideal gambles at that world. All right. So you can think kind of in the general case, what we want is we say the loss at a world I of a set of almost desirable gambles is just the measure, the ith measure of this symmetric difference. And for now we're letting the mu's vary, but you can't really do that, right? That's the thing. It's like the same thing. You have to keep the same measure over the space. And then once you fix a given measure, I still have a notation class for d rho. Rho is just supposed to be a measure instead of a probability distribution. This is what happens when you mash together papers. All right. We'll say an error loss function is D strictly proper if pi always expects its own set of desirable gambles to be lower than any alternative set unless they're almost equal. Meaning they differ only on a set of measure 0. And then here's the Jason's theorem. All you have to do is the measure at I of some set of gambles, how much is that going to lose you at a world, is just the absolute value of if some of the gambles are negative, the absolute value of the gamble at that payoff times by d rho. And right, so rho is saying fixed, and everything has to be mutually absolutely continuous with the Lebesgue measure for. All right. So I think I just kind of point out philosophically I find this cool because we were thinking of scoring rules as measuring the quality of something epistemic, a forecast. But now these conic rules are switching over by looking at the gambles you'd be willing to take, right? The practical gambles you'd be willing to take, and how bad those would be for you. So we're looking for probability at this dual of the function, but in general it's just you give me any set of gambles, if it doesn't correspond to any probability measure, I can still just score it by how do I think that would do? And so it's a real switcheroo. All right. So now what happens? Let's just successfully rush through things. If you expect someone to be more accurate on every conic strictly proper scoring or proper scoring rule, well, in that case you're going to be, and I'll maybe spell this out a little more, you're willing to outsource all betting to that. And what that means in the general case is that if it's just going to be determined by, let's just look maybe at a given, I suppose I'm scoring just a single random variable x. My expectation of x, conditional on Daniel's expectation of x, being at least little x, is at least little x, and same for less than or equal to. If we're in the whole space, if I think Daniel's just absolutely better than I am in every way, then we just need this, right? That for any random variable, conditional on Daniel's being at least x, will be at least x. Okay. We have the theorem. Pi totally trusts P if and only if pi expects P to score at least as well as pi on every conic. So the idea here is, right, if I totally trust you, that's going to be equivalent to expectation of being better on every conic rule, which is also going to be equivalent to saying I'm willing to let you be my agent if you're perfectly aligned. Right? If your payoff is always exactly the same as mine, I will always prefer for you to decide on my behalf. Right? say this, right? So we'll say that like I value Daniel because if I always think his strategy of deciding, like I don't know what it will be, I don't know what his credences are, I don't know what his set of measurable, desirable gambles are, but I always expect it's better for him to do it than for me to do it. And again, we have total trust if and only if value. Right? So there's three-way kind of equivalence between epistemic deference, scoring of gambles, and outsourcing decision making. So I'm just going to kind of give a teaser now, and we need you guys are like good theorem provers and are interested in this. Could use some people. Think of this in like kind of a margins of misalignment. So I'm not going to go into the full detail, but I just kind of want to hint at where I think the next level of generalization is. So this was all kind of thinking, I'm going to score a forecast, right? That was where we started. And we looked at that, and that was like, I'm scoring other forecasts really based on their practical consequences as I kind of expect them to be. And given the utilities are totally aligned, that our payoffs are the same. And then we said, okay, well, when we get to the conic rules, we look kind of more directly at these duals instead of at the probabilities themselves. So we could generalize that now, right? Where we don't say the payoff for a gamble is the same for both Daniel and for me. You think, look, I have n models of the expert. Right, there are n worlds, they're up to n models of the expert. If it's really expert 1, here are the payoffs you would get from a gamble at each world, right? So the rho recommends, the rho is the payoff of the gamble G for expert I at world J. Right? Yeah. So that maybe easier if you just look at it that way. Does this make sense? So, yeah. Right, so these are like all the possible experts and all the payoffs of each world for the expert. And then in the last row is like how this, if I'm just interested in how Ben's doing, how things are looking, right? So it's an n plus 1 by n matrix.
Sorry, could you say what the two columns are?
So the idea is, I think Daniel really could be agent 1, 2, 3, 4, 5, 6, 7, 8, 9, or n, right? Because they're n worlds, so there are n ways he could be, up to at most n ways. And then I also, I don't know what his beliefs are, I don't know what his utilities are, but so there's some gamble, right? And it could be like, he gets, a car at world 1, and I get a donkey at world 1. He gets a house at world 2, and I get, killed at world 2, right? Like that would be like a gamble, right? And I was like, these could be, and so it's going to specify for each potential agent what he gets or she gets at that world. So I think so. You first.
Is the number of experts and the number of the worlds the same?
I mean, that's sort of the max, right? So you could have duplicate experts, so there could be some rows that are just duplicates.
I think a useful thing is we think like there's one agent you're considering to deferring to, but you don't know what their gambles are from their perspective. You're uncertain about that, and so they're kind of like the possible ways the expert could be, and those depend on the world. And so if there are that many worlds, then there's that many. Since Ben is uncertain about what my gambles are, there's at most n possible different ways I could be, since how I am depends on the world, because the world specifies everything.
Right.
But the world also specifies what we each win. And so that's why they're n in both ways, right? Ben is uncertain about both what Ben will get or what either of us will get, but also how I value what I get.
Yeah. Is that? Oh, and then.
That was my question.
Okay. Yeah. So like the idea is if I'm looking at a set of desirable gambles and I want to score a potential expert that I might want to outsource decisions to, I don't really have to look at the expert's actual possible credences or the utilities from the expert. I can just score it according to like how the potential sets of desirable gambles all look from my point of view. Right? So like Daniel could be like way smarter than I am, but if he's picking gambles that result in me like losing at every world, it's as if he's a really dumb agent with my utilities. Right. So that's the idea. It's like it's as if these people were dumb, or rather than and making decisions on my behalf. Right. So you kind of go back and forth between. It doesn't kind of matter how the sausage gets made, whether it's from the epistemic perspective or the practical decisions. It's just kind of how these payoffs look from me and me scoring the sets of gambles, desirable gambles, but looking just at this last row. Right. So yeah, this is kind of just the initial teaser, right? So the expert, let's say the expert's coherent, really smart, going to take G in worlds where PW, the expert at world I dot GI is G. Oh, GI dot, yeah, sorry, that's right. I got it right, okay. Is greater than or equal to 0. And you can think of scoring the expert from pi's perspective. Right? You can think of special cases of how would this look when it's just a rotation of my utility? How would it look if we're kind of subtracting a constant? How would it look if it's a squiggly, but maybe bounded by something I would value? And that's kind of the thought, is thinking how much in general could I tolerate in trade-off smarts for misalignment. Right? So these are the main things you want to throw in. When would you value an expert, even though the expert is misaligned? Again, valuing meaning willing to outsource decision making, willing to always let the agent the expert act as your agent on your behalf, even though there might be some misalignment. Right? We kind of do that already to people. Right? Sometimes it's okay. What the trade-off will be between accuracy and misalignment. So if you're way smarter, then sometimes I might be actually willing, under certain circumstances, to take more misalignment in some way. But other times maybe not. So you see if you can characterize that. And for a given scoring rule, if you kind of fix a distribution over the possible gambles you'll face, when misalignment would be tolerable, even if you don't in general value the expert. Wow. Okay. Looks like there's time for one question. Yeah.
I'm wondering if there's an obvious relationship between the trust properties you were talking about, the kind of Vingian tiling stuff that Aaron was interested in, or?
Oh, I didn't see the Vingian talk, so
Okay.
I don't think there's gonna be any kind of Lobian thing here because it's gonna be pretty simple.
There is no lobe in my talk.
There's no Lobian. Okay. So maybe there's more relationship. Yeah. Anything else? Okay.
Yeah, so I guess I'm thinking about this last point that you made of in some cases if the agent is smarter, we might accept more misalignment and comparing this to the alignment problem. And
Yeah.
Obviously it would be really great if we had some pretty general result like that. I'm imagining maybe this is not the case because the kind of concern that we have is agents that are so smart that they have kind of options that we didn't even conceive of for maximizing their own utility
Yeah.
and throwing ours under the bus. And if there's an option like that on the table that's you get astronomical utility for the agent but not for the then it's then probably this isn't going to hold.
Yeah. I mean, you could think of it as some cases where there would be a guarantee. So if for instance I knew you were omniscient and your utility always preserved the orthant where the gamble, right? So if it's if a gamble is positive for me at world I, it's going to be positive for you at world I.
Yeah.
Right? But maybe very different. Right? There I would still value you even if you were very misaligned, but everything kind of stays in the same orthant.
Yeah.
If you ever take dominated gambles from my perspective, right? If that's possible, I would not value you, but I might be willing to still let you decide, depending on my measure, right? Because if I were really confident we're being this denominator region, I'd be like, no way. But if I thought that was very unlikely, I would, right? So you can give them with like examples like that.
Yeah.
When you start adding like, complication, to the model of like we're not perfect utility maximizers, or we're not in this S5 luminous space of knowing all the possibilities, then things get more.
Yeah. Another one we thought like very little about, just as an idea to explore possibly the future, is maybe I think that the decision problems I might be faced with are different than if I defer to you. And that could maybe capture
Right,
something
right.
like a capability difference. Right? So maybe I think I'm making decisions, I'm just not gonna be able to take
Yeah.
these extreme gambles.
Yeah.
But if I defer to you, maybe actually the underlying distribution, from my perspective of the gambles that you would be able to face, is really different. And maybe that includes more extreme things.
Yeah.
So is a direction you could generalize and you just, it makes things more complicated, maybe it's worthwhile, but we haven't done any thought past this suggestion. But that seems like one way to introduce a capability difference, not just a kind of you're much more informed than me kind of difference.
Yeah.
Yeah, we wanted to get some basic, stuff proven in the easiest cases first.
Yeah.
Should we get